All right, welcome to the third part of this whole series of 4.2, and I'm trying again to break these up in a much smaller chunks. So in the previous section, we kind of talked about the theory that found these three essentially equations that we need specifically to project onto a line. And we're going to essentially follow these steps here for this example, where this example is taken from the textbook. We're going to project the vector B onto this vector A. And then from here, we should then be able to find a general projection matrix P now that we can project any vector B onto this line 1, 2, 2. Essentially gives us that projection matrix. Almost called it a transformation, which isn't right, but that projection matrix. So that's essentially the process. And again, what's going to be really nice about this is that we're projecting onto a one-dimensional space, but we can take this and extend it to larger spaces and higher dimensions. So to walk through this in terms of the numbers, again, you see the work in the textbook. I'm going to kind of work out how you see it in my notes. But the very first thing we need to do is we need to find the projection vector that is created from projecting B onto A by first finding x hat. So we need to find A transpose B and A transpose A. So I'm going to do A transpose B first. So A transpose B is 1, 2, 2, and then 1, 1, 1. This is essentially telling us that we're just going to add these three entries together. So 1 plus 2 plus 2 gives me 5. So there's my A transpose B. And then A transpose A is really just looking at the magnitude of this vector, the original length. But just to write it out, 1, 2, 2, 1, 2, 2. I'm essentially squaring each of these numbers and then adding them together. So 1 squared plus 2 squared plus 2 squared, this gives me 9. So I have A transpose A is 9, I have A transpose B is 5, so this gives me x hat is 5 over 9, and telling me then that the projection vector, so the projection of B that goes onto A is 5/9 of A. That's my projection vector. And what I can do with this now is I can take this and I can solve for that error vector, the orthogonal piece, that takes me from A, or this P projection essentially, back to B, if we were kind of creating the triangle that I had up here for the second part of the video. And so to do this, we're just going to go through and take B and minus our projection vector that we found. P is 5/9 of A, which is 1, 2, 2. So just writing this out, specifically, I have A as 5/9, 10/9, and 10/9. And I said A, but P. Sorry, my projection there. And so let's go through and let's solve for E. So I'm going to erase our work here. And remember, our whole setup is that B is equal to E plus P. So that's where this equation again came from. So we're using that relationship to solve for that error vector. So B is 1, 1, 1. If I subtract from that 5 over 9, 10 over 9, and 10 over 9, I get my error is 4/9. Here, -1/9, and -1/9. And remember that this error vector that we're finding here, this is perpendicular to P. And so if I was to dot these two things together, we should get 0 as an answer. And you'll notice 4, 5 is 20 over 81, minus 10 over 81, minus 10 over 81 gives us 0. Dot product is 0, these are orthogonal. If I take E, E is also orthogonal to A, so I can do E dot A, and I will also get 0 if I was to perform that. And you can do a quick check. You'll see again the algebra in the textbook. 4/9 minus 2/9 minus another 2/9 again is indeed 0. So this is matching again what we see geometrically. And again, this is specific to this vector B. And if I find the magnitude of this will tell us how far off our answer is, how far away the projection is from B. And so again, this is really, really helpful. This is example 1, but if I want to change my B, then the projections and all of this would necessarily change. And so we don't want to have to do this for every single vector B that we have. So what if we can find a projection matrix so that no matter the B, we can find the projection and ultimately then find E from that immediately. And so I want to find my projection matrix, which is A transpose over A transpose A. And this is getting into example 2 because in example 2, we're not relying on a B. All I need is my vector A that we're projecting onto, and then we can take any vector B and again find that projection immediately. And so I'm going to go through now. We know A transpose A is 9. So what we really need to go through and do is to set up our A transpose so we can find our matrix. So I'm going to take A, which is 1, 2, 2, and I'm going to multiply this with 1, 2, 2. And again, this is going to create a 3 by 3 matrix where the first row is just 1, 2, 2. The second row is double. This third row is double. So again, this is a rank 1 matrix. And it's really clear that you can see that this is rank 1 because these are just scalar multiples of the first row. And which is also really important because remember, we're projecting onto a one-dimensional space. So this matrix, the column space here, this is what keeps us in A. Now, this is just that first part of my projection matrix. So to finish this off, to find that projection matrix, I need to divide everything by 9. So 1, 2, 2, 2, 4, 4, 2, 4, 4. Here's my projection matrix. Here. And so now what we can do is if I was to take B and multiply it with this, this would find our projection matrix that we had earlier, our projection vector, excuse me. But now that I can change B to be anything, we could figure out what the projection is on A just by using this matrix here. And the book kind of gets into kind of a conversation around these projection matrices, which I think is interesting, which is the fact that if I take this projection matrix and I multiply it with itself, then I'm not going to change anything. And that makes sense because if I project onto the line and then try to project again, we're already on the line. So we're not going to go anywhere. And then if I look at I minus P, so if I take this and I subtract it from the identity matrix, that's the idea is a reflection. We drew B so that it was above A, almost like a positive rotation. But if I wanted to go the exact opposite and do the same projection, this is the I minus P. It's just giving me if my angle is below in terms of the rotation. I think the takeaway, again, is that this projects into one subspace, this projects into the orthogonal subspace. This would be essentially orthogonal to one another. And this is projection onto a line. So in the next set of videos, we're going to project onto a subspace, so we're going to kind of extend this. And so you can kind of see how performing this kind of linear algebra work. We've seen it before, but we'll start dealing with matrices. And ultimately trying to be able to project a matrix onto a subspace, any size space, creating that n by n or n by n overall. So let me know if you have any questions. Hopefully this helps, specifically with projection onto one-dimensional subspace.